Okay, welcome back everyone to these tutorials on the theory of computation. So in this tutorial, we're going to be looking at another example of designing a context-free grammar. In this case, this is the exercise. So I want to show that the following language L is context-free. So to show that a language L is context-free, there's two things you can do. You can either give a context-free grammar that generates L, or you can give a PDA that accepts L. In this case, I'm going to design a context-free grammar that generates L. Um, and just for simplicity, I'm going to assume that I don't need to prove the correctness. So no proof of correctness needed. However, in some cases, like in assignment 2, you're going to have to prove the correctness of a designed context-free grammar, and I'll show you how to do that in another video. Okay, so we want to, in this case, though, we want to design a context-free grammar which generates this language L. So how are we going to do this? Well, we're just going to use this intuition that we've started to build up about context-free grammars and grammars in general, trying to capture the sort of recursive nature of languages. So what is the kind of recursive nature in this language L? So notice what L is. L is really just the set of even length palindromes, right? Palindromes are strings where if you read them from left to right and from right to left, they're the same string, right? And so these are even length palindromes because I have, the length of W and then the length of W twice. So I have two times the length of W. So of course that means that I have a string of even length, right? So for instance, I have something like AB, BA, ABA, ABA, ABB, BBA, right? And so on, right? So where this is the first part of the string and this is the second part of the string. So if you wanted to design a context-free grammar that generated this language, you might be tempted because you might still be sort of in the sort of DFA, NFA mode, you might be sort of tempted to try to generate the string from left to right somehow. So to create production rules where you start by generating the left half of the string and then you continue by generating the right half of the string. That's not going to work in this case, right? It's not going to work in this case because the property of the strings in this language are that there's sort of a dependency between the sort of first letter and the last letter, between the second letter and the second to last letter, and so on, right? And so this is why this language, if you were to try it out, you could show that it's not regular, right? Because you could just use the pumping lemma to show that you could sort of find a pump where you could get a pumped string that's not an L. But just the intuition behind why it's not regular is because you kind of have to remember, right? You have to remember this A for an arbitrarily long amount of sort of intermediate letters and then check that this A is sort of there in the corresponding position, right? So you need some like infinite amount of memory, which FAs in general can't provide. Um, but context-free grammars can kind of get around this with sort of describing a recursive procedure, right? So all this to say that it's probably not a good idea if I start generating rules that look like, I don't know, like S gives me AS or BS. And then I say, oh, well, let's assume that S is also a palindrome. That's not quite going to work because, then I get into the situation of I can generate A and then maybe BB. And so then I don't get something that's a palindrome. So essentially what I want to do is I want to, at every step of the way, ensure that I'm maintaining this palindrome constraint, right? So how do I do this? Well, the easiest way to do this is to start with the base case of what's the sort of simplest string that's in L, right? And so the simplest string or the simplest strings, that's the same thing, or the simplest strings in L, those are going to be the ones that are going to be in my base case, right? So the base case are the base case is for strings that um, you can't use the recursive sort of call to generate, right? Because at some point your recursive call has to stop, otherwise you can't generate any string. And so in this case, that simplest string is just going to be the empty string, right? Because the empty string has, right, the length of the empty string is 0. It's the unique string that has length 0. And of course, it's a palindrome, right? Like if you take um, sort of something that's empty, right, and you read it from left to right and from right to left, it's the same, right? And so it's a palindrome and it has even length because 0 is even, okay? So that's going to be my production rule for the base case. Now, what is it going to be for the recursive case? Well, like I said, you want to avoid trying to generate the string sort of left to right. Instead, you kind of want to capture the fact that if a string is a palindrome, then what that means is that this sort of letter, this first letter, is going to be the same as this last letter, right? So if you know that S is going to sort of generate a string W reverse, then how can you create a slightly larger string that maintains this sort of palindromic nature? Well, what you can do is you can say, well, maybe I have some palindrome like um, ABBA, and to create a slightly larger palindrome like AABBAA, I just add an A at the front and add an A at the end, right? So that would just be something like A at the front and A at the end. And so that's my first production rule, right? And then my second production rule in the recursive case would just be the other letter in the alphabet, right? So for B, right? So I would get S gives me B, S, B, right? And so that's really going to be it. That's going to be the context-free grammar. So the production rules in my context-free grammar G, where the only variable is going to be S, the terminals are going to be A, B. So the production rules are just going to be S gives me epsilon as well as ASA, whoops, ASA, and BSB, right? And so if you don't believe me that this is going to generate palindromes and only palindromes of even length, then we can just sort of test this intuitively. So suppose I have, maybe this palindrome. I know that it starts with an A and it ends with an A, so that's the first production I'm going to use. I'm going to say A and then SA. And then I just need to generate the rest of the string, the middle part, right? So S, I'm going to replace with this production rule. So this right-hand side, so it's going to be S, then B, S, B, and then A, right? And then again, I'm going to replace that with the BSB right-hand side. So that's going to be A, B, and then BSB, and BA, okay? And then finally, I'm just going to replace, like I'm sort of done using the recursive call. Now I'm just going to terminate and say, I'm just going to replace S with the empty string, right? So I'm going to replace this with epsilon. So then I'm going to get A, BB, BB, A. And this is going to allow me to generate any even length palindrome, because any even length palindrome can be exactly described this way, right? So if my alphabet is AB, then the palindrome has to either start with A and end with A, or start with B and end with B, and its middle has to also be a palindrome. Otherwise, the entire string wouldn't be a palindrome. Okay, and so that's how you create a context-free grammar to generate this language. And so this shows, um, barring an actual proof of correctness. So a proof of correctness would be required if you wanted to sort of rigorously show that this proves that L is context free, but for our purposes, for our purposes of this exercise, that's good enough to show that L is context free.